Dear students, welcome to a new video for the sampling subject. Now we will move to the very important part for the variances of the estimates. The variance of the estimate yi in a finite population is usually defined as sigma square for the summation of yi minus y power all square over the total population n. As a matter of notations, results are represented in terms of slightly different expressions, in which the divisor n minus 1 is instead of n, we take s squared equal to the summation of yi minus y capital Y power all to the power 2 over n capital minus 1. This convention has been used by those who approached sampling theorem by means of the analysis of variances. Its advantage is that most results take slightly simpler form, provided that the same notation is maintained consistently. All the results are equivalent in either notations. We now consider the variance of y small power by this mean, which is the expected value of small y power minus capital Y power all square, taking overall the n combination and samples. Here we will take theorem 2.2. The variance of the mean y power for a random sample is v of y power equal to expected value for y power minus capital Y power square equal to s square over small n multiplied by capital N minus small n over capital N, which is equal to s square over n multiplied by 1 minus f, where f equal to small n over capital N, which is denoted for the sampling fraction. We can prove this theorem by the following steps. Let's take n as the common factor for y power minus y power, so the summation for y1 minus y power plus y2 minus y power up to yn minus y power. Per the arguments of the symmetry used in relation 2.5, it follows that the expected value for the difference between y1 minus y power all square up to yn minus y power square equal to n over capital N times all these values, and also that the expected value for y1 minus y power times y2 minus y power plus y1 minus y power times y3 minus y power. Okay, this all for the end n minus 1 minus y power times yn minus y power, all this equal to n times n minus 1 over capital N times capital N minus 1 as a common factor and all the other values inside the brackets. And we set this step as 2.11. In 2.11, the sums of the products extended to overall pairs of units in the sample and population respectively. The sum on the left contains n times n minus 1 over 2 terms, and the right side includes n capital minus times n minus 1 over 2 terms. So now we can square 2.9 and average overall simple random sample using 2.10 and 2.11. Substituting, we obtain n square expected value for y power minus capital Y power square equal to n over n multiplied by y1 minus y power all square plus y2 minus y power all square up to y capital N minus y power square. And this is the beginning of the brackets, and the middle term will equal the first term times second term multiplied by 2. So the second term will be 2 times n minus 1 over capital N minus 1. And finally, the third term will be y for the yn minus 1 minus y power times yn minus y power. Completing the result, the square of the cross product term, we have n square expected value for y power minus capital Y power square n over n 1 minus n minus 1 times over n minus 1, and the same second and third term the same. The second term inside the bracket, since the sum of the yi equals to capital N y bar division by n square, this gives us in the theorem where v, which is the variance for y small bar, equal to the expected value for y small bar minus capital Y bar all to the power 2, which is equal to n minus n over n small capital multiplied by n times n capital minus 1 multiplied by the summation from I equal n up to capital I, the difference between yi minus y bar all square, which is equal to s square over n times n capital minus n over m. And this is complete our. Now we have three correlates. The number one, the standard error of y bar is sigma y bar, which is the root for sigma square. So the rule is s divided by root n multiplied by root n minus n and divided by capital N, which is equal to s divided by root n multiplied by root 1 minus f. The second is the variance of y hat. Y hat is an estimate of the population total y, which is equal to capital N multiplied by y bar small. Variance for y hat equal to expectation y hat minus y all to the power 2, which is equal to n square s square over n multiplied by n minus n over capital N, which is equal to n square s square over n times 1 minus f. Finally, the standard error of y hat is the root for the previous equation, which is equal to n times s divided by root n multiplied by root n capital minus n small over capital N, which is equal to capital N times s over root n small multiplied by 1 minus f. Now let's move to the finite population correction. For a random sample, a size n for an infinite population is well known that variance of the mean is s squared over n. The only change in the result when the population is finite is the introduction of the factor capital N minus small n over capital N. The factors capital N minus n over capital N for the variance and the root for this for the standard error are called the finite population correction, which is the abbreviation FPC. They are given with a divisor, which is n minus 1 in a place capital N, by writers who present the result in terms of sigma, provided that the sampling fraction small n over n remained low. These factors are close to unity, and the size of the population as such has no direct effect on the standard error of the sample mean. For instance, if S is the sum of the two populations, a sample of 500 from population of 200,000 gives almost as precise as an estimate of the population mean as a sample of 500 from a population of 10,000. Persons unfamiliar with the sampling often find the results difficult to believe, and indeed it's remarkable. To them, it seems obvious that the information has been obtained about only a very small fraction of the population. The sample mean can't be accurate. It is for the reader to consider why this point of view is erroneous. In practice, the FPC can be ignored whenever the sampling fraction doesn't exceed 5%, and for many purposes, even if it's highly as 10%, the effect of ignoring the correction is to overestimate the standard error of the estimate y bar. The following theorem, which is an extension of the theorem 2.2, is not required for the discussion of this chapter, but is proved for the later reference. Theorem 2.3. yi and xi are pair of the variables defined on every unit in the population y bar and x bar are corresponding means for the simple random sample of size n, then their covariance. So expectation y bar minus capital Y bar times expectation small x bar minus capital X bar equal to n minus n over n minus n, over n times n multiplied by 1 over capital N minus 1 multiplied by the summation for y minus y bar times x minus x bar. This theorem reduces to theorem 2.2 if the variance are equal on every unit. Let's take the proof of the theorem. Applying the theorem 2.2, the variance yi equal to let ui equal to yi plus xi. The population mean ui is u capital bar equal to y bar plus x bar. So we can substitute in theorem 2.2 and get expectation for u bar minus y bar square equal according to 2.2 equals this form. So that the expectation of by substituting again u small bar and u capital bar, we get the rule 2.60. Explain the quadratic terms on both sides by theorem 2.2, we get the expectation proof for y bar minus capital Y bar all square. With a similar relation for the expectation y x small bar minus x capital bar square, hence these two terms cancel on the left sides of 2.16. The result of this theorem follows from the cross product terms. Thanks for listening to this lecture, and we join again in another lecture.